Good morning, everyone. Today, I'll present our work on D²PPO, which addresses a critical problem in diffusion-based robot policy learning through dispersive loss regularization. Let me start by introducing the core problem we identified: diffusion representation collapse. In diffusion policies, we discovered that semantically similar observations are mapped to nearly indistinguishable features in the hidden space. This phenomenon severely limits the policy's ability to distinguish subtle but critical differences required for precise manipulation tasks. As shown in our analysis, this representation collapse leads to poor performance on complex manipulation tasks, where the policy fails to generate context-sensitive actions despite having powerful generative capabilities. First, the pre-training stage uses vision transformer for feature extraction and applies dispersive loss regularization to prevent representation collapse. The dispersive loss treats all hidden representations within each batch as negative pairs, encouraging feature diversity. Second, the fine-tuning stage employs policy gradient optimization using a two-layer MDP formulation for environment interaction, building upon the enhanced representations from pre-training. This two-stage design allows us to combine the generative expressiveness of diffusion models with goal-directed precision of reinforcement learning. In stage 1, we augment the standard diffusion loss with dispersive regularization. L_D²PPO equals L_diff plus lambda L_DISP. We implement three dispersive loss variants: InfoNC L2, InfoNC cosine, and hinge loss, each derived by removing positive pair alignment from traditional contrastive learning. In stage 2, we optimize the enhanced diffusion policy through reinforcement learning, using importance sampling to efficiently compute gradients across the denoising chain while preserving the representational structure from pre-training. Our pre-training experiments demonstrate significant improvements across all tasks. Let me walk through these four key findings. First, D²PPO consistently outperforms baseline D²PPO across all four robotic manipulation tasks, with larger improvements on complex tasks, achieving 36.2% improvement on the transport task. Second, the distribution of improvement rates across different dispersive loss variants shows higher variability but consistently positive trends for complex tasks. Third, our method suitability analysis reveals that 5 dispersive loss variants show task-specific performance patterns, with InfoNC L2 late achieving best results on complex tasks, highlighting the importance of hierarchical regularization. Finally, we observe a strong positive correlation, our superscript 2 equals 0.92, between task difficulty and maximum improvement rate, demonstrating the importance of representation quality for complex tasks. Moving to our fine-tuning results, we see that D²PPO maintains its superiority after policy gradient optimization. The learning curves show that D²PPO achieves faster convergence and higher final performance across all tasks. Most notably, on complex manipulation scenarios, D²PPO shows substantial improvements. Square task performance increases from 47% Gaussian to 80% D²PPO to 90% D²PPO, while transport task progresses from 0% to 60% to 85%. Our comprehensive comparison table shows that D²PPO achieves state-of-the-art performance, ranking first overall with an average success rate of 0.94, representing a 26.1% improvement across the 4 tasks compared to existing methods. To validate practical deployment, we conducted real robot experiments on a Franka Panda manipulator. Our sim-to-real transfer results demonstrate successful performance across all tasks. The enhanced representations learned through dispersive pre-training maintain their quality when transferred to real-world scenarios, and the complete D²PPO framework achieves stable manipulation capabilities across all benchmark tasks. This confirms that our approach not only works in simulation but also translates effectively to real robotic systems. Now let's take a look at the real-world experiments using the Franka Emika Panda robot. On the left, we show task executions with our method, that is, diffusion policies trained with dispersive loss. As you can see, the robot successfully completes all 4 manipulation tasks: lift, square, can, and transport. These results demonstrate that our approach enables the policy to robustly generalize to diverse real-world scenarios, even under challenging conditions like object occlusions and dynamic viewpoints. In contrast, the right side shows performance without dispersive loss. Here, we observe clear failures in both the square and transport tasks. The robot either misgrasps the object or fails to coordinate the dual-arm handoff, leading to task termination. These real-world results validate the practicality of our approach and highlight the importance of representation regularization in diffusion-based policy learning. With dispersive loss, the policy learns more discriminative features, leading to consistent success in high-complexity tasks. Thank you for your attention. To summarize, we've introduced D²PPO, which addresses diffusion representation collapse through dispersive loss regularization. Our two-stage framework achieves state-of-the-art results with 22.7% improvement in pre-training and 26.1% improvement after fine-tuning. The key insight is that representation quality becomes increasingly critical for complex tasks, and our dispersive regularization provides an elegant solution without requiring additional parameters or external data. I'd be happy to take your questions.